So now we're going, excuse me, now we're going to look at rates of change. Rates of change are really a major focus in calculus. And you're used to actually finding rates of change, but what you're used to find are what are known as average rates of change. So if we're thinking about this over a period of time, this would be a rate of change over a time period. So the way you found speed or velocity in grade school science classes are a very good example of an average rate of change. And what it is let's say I have here a graph. We could say that y stands for for position and my x is the time, in which case the rate of change of this would be velocity. And if I wanted to find the average rate of change between 1 second and 5 seconds, what I would need to know is where are we at 1 second and 5 seconds, in other words, the positions, and subtract those and then divide by 5 minus 1. In other words, if I were to connect those 2 points, I would have a secant line. Remember, a secant line intersects an arc at 2 points, and I'm just finding the slope of that line. So it would be the y value at 5 minus the y value at 1, change in y's, over the change in x's. And that part of finding an average rate of change is something you're used to. So for example, if I were to give you a function x cubed minus x, and I wanted to find the average rate of change over the interval from 1 to 3, well, because it's an average rate of change, I do f of 3 minus f of 1 over 3 minus 1. Well, if I plug in 3, 27 minus 3 is 24. If I plug in 1, that's 0. And this is going to give me 12. So over the interval from 1 to 3, f has an average rate of change of 12 units for y per units for x. More complicated, though, is what if we wanted an instantaneous rate of change? And this is one of the reasons why calculus was actually created, was that average rates of change are fine, but for a lot of things, especially in the sciences, we need to know an instantaneous rate of change, which is at one specific moment. So if I'm thinking of this graphically, instead of finding the slope of a secant line where I know 2 points, I have a tangent line. And remember, a tangent line intersects an arc at 1 point, and I want to know the slope of that line. And so the way this is approached is we say, well, I know I have this point. I'm going to say it's at A and y of A. And I'm going to go ahead and pick a point that's just a little bit over to the right and say that that's h to the right of A. So this distance right here would be h, which means that my x-coordinate is A plus h. Well, then I have a point there at y of A plus h. Now I don't know what h is. I just know it's how far to the right I am of my A value. That is where I'm looking for an instantaneous rate of change. But now I do have 2 points that I can find the slope between these 2 points, which would be y of A plus h minus y of A over A plus h minus A. But now I don't want the slope between 2 points. I want the slope at 1 point. So what I want to do is move these 2 points to be closer together. And if they're closer together, that means that h is getting smaller and smaller. In fact, h is approaching 0. And this idea that h is approaching something is the idea of a limit. And this is where all this limit work we've been working on is we want to then take the limit as h approaches 0. So this part right here is finding the slope between 2 points. And the limit as h approaches 0 is saying, let's move those 2 points so close together that we can't tell that they're 2 separate points. It will, for all intents and purposes, be 1 point. This is instantaneous rate of change, and that is the slope of our tangent, or what you will sometimes see it called as slope of a curve. There is actually a third name for it, which we will be getting to in a future unit here. So if, for example, I wanted to find the slope of a tangent for the function x squared at the point 2, 4, well, we'll get to the fact that an equation of a tangent in a second, but for an equation, I need slope and point. We're already told the point is at 2, 4. To find the slope, I want to find the slope at f of 2, but then I'm going to subtract f of 2 plus h, which is just a little bit to the right of it, and 2 plus h minus, whoops, I made a mistake there. I had switched things around. I want to take the point just to the right, take away the point at 2, f of 2. But then I want to move these 2 points infinitesimally close together, and so I do the limit as h approaches 0 for it. Well, if I plug 2 plus h in for f, haven't found the limit yet, so it's still the limit as h approaches 0. I have 2 plus h squared. I know f of 2 is 4. The 2's in the denominator cancel, leaving just h. Well, if I try substitution here, I end up with 0 divided by 0, so substitution is not going to work, so I'm going to go ahead and try simplifying. So I still have the limit as h approaches 0 because I haven't evaluated the limit yet. What I notice now is that on my numerator, 4's cancel, and then I can actually divide my numerator by the h in the denominator, and I'll have the limit as h approaches 0, 4 plus h, and this I can now do substitution on, so if I plug 0 in for h, I get 4. So the slope of my tangent is 4. I know that we're going through the point 2, 4. The equation of a tangent is the equation of a line with slope 4 and going through the point 2, 4. Well, if we use point slope form, that would be y minus 4 equals the slope times the quantity x minus 2.